It's always weird to hear your own voice. Hello and welcome everyone. I hope you had a great lunch. You're not too tired because in the next 45 minutes we are talking about expecting the unexpected and graceful error handling. My name is Bastian. I work at a company called ResearchGate in Berlin. It's a social network for scientists where scientists can upload their research data, collaborate with other scientists and revolutionize the world. It has over 14 million users of 190 countries, and we are having around 1,800 requests per second on average. Also lots of data with 100 million publications, over 140 components, services that run somewhere, do something. That was in 400 Git repositories and about 80 engineers. We have growing traffic, active development. We're doing continuous delivery with like 50 deployments per day or something like this. That means we constantly change something. Why am I telling you this? Not to brag about numbers or so, but to illustrate that if you change something and if you have constantly changing things, that also something will go wrong at some point. That means with a deployment, someone is going to introduce a bug, even despite all the testing. You may have performance regressions because something is slower than expected. Just because of growing traffic, you may have database overloads. Some of your servers, some of your hardware may fail. And just because of maybe microservices and distributed systems, which are sometimes kind of hard, where you have a network in between that can be problematic, or where you just have multiple technology stacks, the complexity can rise and can increase. That means if you have a non-trivial application somewhere, errors will happen. And you have to just count that in. So this talk is going to be about how to detect that something is breaking and how to handle these errors if they are breaking in a way that the user does not notice them, or hopefully does not notice them. So let's start with detecting if something breaks. For that, we need to talk about logging and monitoring. Let's start with logging. Because logging is quite really important to see what is happening in your platform. Because you don't want to show a stack trace to the user, so you don't want to have that. It's a bit hard to read, but it's some PHP error somewhere. This is really bad. Ideally, you want to have something like this, like a nice error page that just tells the user, okay, something is broken, but not exactly what. And then you can look in your error logs to see actually what broke. What was the stack trace? What was the exception? What is really useful there is not log only the exception with the message and the stack trace, but also as much additional information as possible to help you analyzing the problem as quickly as possible. So for example, if you see this error page here, and usually what happens if a user or a colleague of yours is seeing this page, they are going to make a screenshot and send this to you saying, hey, something broke. What you're seeing here is that we, for example, print an error code in here. This is some additional information that you can also log with the exception that resulted in this page to be shown. So if you get the screenshot, you can just get the error code, search for it through your logs, and then you'll find out what the actual exception was. But it's not only that, it's also all kind of other information from the request where this error originated from. For example, you could add the IP of the user. You could geolocate the IP to see where the user was coming from. The user agent, user ID, session ID, the actual URL of the request that did this exception, the HTTP method, request headers, everything that can help you analyze the problem. And since you hopefully don't have like 5,000 exceptions per second, you can also be very verbose with that. Because hopefully the amount of exception you're having is like low and can be fixed. Additional thing with logging is that it's very beneficial to log in a structured way. Of course, it's very nice to make logs human readable, but the problem with human readable log formats is that machines can't understand them. And a lot of the aggregations I'm talking about in a few minutes is that for that it's important that machines can also understand the logs. What we find out is a good way to log in a structured way is in JSON format, because the overhead of the format is very low in terms of additional characters, and there is like a parser and a JSON dumper in any kind of programming language available. So regardless if you're doing Ruby, PHP, Python, Java, whatever, there is something that can write and read JSON. Even on the command line, you can have JSON parser with JQ that makes the log then human readable again if you tail over the yogs. Let's talk a bit more about microservices. Because with microservices, you are not running one service that produces one error log, but you're running multiple services. So a bit abbreviated, it could look like this. So you have a user request coming in here, you have maybe some gateway service for your API or for your web front end that produces logs, and this gateway service then calls all kinds of other services in your architecture that also produce logs. What would be very nice is that if something is breaking here, probably also something is breaking here, and these all produce logs to be able to correlate this with each other. For that, it's a good idea to introduce a correlation or tracing ID into your architecture. How does it work? So the first time a request from the outside, from a user or from an API comes in, you create a unique tracing ID for this request, just like a UUID. And this unique tracing ID you transport over request headers to every service that you're calling. If you have looked at the talk about Istio, for example, earlier, this is, for example, what Istio also gives you for free for you. But also you can, of course, do this in your own stack as well. And then every time you're logging something, you include this tracing ID in the logs. So at the end, if you want to see all logs from one incoming request, you can just search through all your logs for this ID and you get all log messages. Which brings us to actually getting to the logs. Because usually your architecture and your environment is not looking like this, but more like this. So you have multiple instances, multiple servers of something. Which means, of course, I can SSH into all the servers, tail over the logs, use grep and whatever kind of Linux or Unix tools I can use for this analysis, which quickly then will look like this. And that's not really usable and user-friendly anymore. Also, I maybe don't want to have give every one of my junior developers in my team SSH access to the servers to analyze logs. Maybe that's not a good idea. So it makes sense to put all these log messages in a central place and make them easily full text searchable so that I can just search, for example, for this error code or this correlation ID and see all log messages, and also through that make them aggregatable. There are tons of ways to do that. One thing that is very common there is the so-called ELK stack, which stands for Elasticsearch, Logstash, and Kibana, which offers a central place to store all your log messages and make them full text searchable. And it supports structured messages with multiple fields. A setup could look like this. So you have all your servers where some services and applications are running on. They produce logs, so they still log to file. And then on every server you have a small Logstash daemon running that tails on the logs. Then sends this to some RabbitMQ instance for load balancing, and then you have another Logstash instance tailing on this RabbitMQ instance and doing some parsing, some tagging, whatever you want to do there. So Logstash is very powerful in that, and then it writes this to an Elasticsearch instance, so you have the logs stored somewhere. The reason why in this setup you would have a RabbitMQ queue in between there is that in the case of an error, it's very likely that the amount of logs per second is increasing rapidly. And in this case, you don't want to overload Elasticsearch by having like 5,000 writes a second onto Elasticsearch. Because while Elasticsearch is very powerful and can handle a lot of writes, at some point also it doesn't scale anymore. On the other hand, if you are in an error condition and you have the amount of log messages, it's very likely that all the log messages look the same, kind of the same anyways. So it's fine that you don't have the really current ones from like a second ago. So it's fine if they are a minute older or something like this. So RabbitMQ is very good at buffering all of that for you. A word about Logstash. If you don't know, this is like a small daemon. It basically works in a way that it has an input, which can be, for example, log file or RabbitMQ, some filters where you can pass a message, tag it, and do all kinds of interesting things with it, and an output, which would be, for example, an output to Elasticsearch. And for that, it has a very rich plugin system. It's a very useful tool, so I encourage you to look into that. There's also a more modern way for this stack with also a product from Elastic, the company behind Elasticsearch, called FileBeat. Because with FileBeat, you can have a FileBeat daemon running there, which basically also just tails on the logs and forwards them to a Logstash for additional parsing and filtering. Though the difference is you don't need a RabbitMQ instance anymore in between there because FileBeat already has support for back pressure detection. So if this Logstash and Elasticsearch is getting too many messages, FileBeat will notice it and then throttle itself automatically. So that makes it operationally less complex because there's one component less in there. And then the last part of it, Kibana, is just a front end for Elasticsearch, which can give you dashboards and where you can query your logs and full text search through your logs. Having said all that, always log to file as a backup. because chances are also, if you need it the most, your central log management system will also sometimes go down. Of course, you should be able to scale that, and you should be able, that should be reliable, but at some point this also may break, and probably in the case where you need it the most. So you should always have the backup of having some files where you could, in accidents, look at to. But there are not only exceptions that can impact the stability of your web application. There are also performance regressions, something just getting slower, which is not good. And there are also conversion regressions, because you are introducing a new feature and for some reason people are not using that anymore, or using it less than they were before. So if maybe you broke the sign up and now only 10% of the users that want to sign up actually managed to go through the sign up for some reason. Or you have traffic regressions where you just check the amount of traffic drops tremendously because you broke a link also. For that, you need additional monitoring. And we're interested in monitoring, especially on latency. How long did something take? Availability. How available is it? How many requests were actually successful, percentage-wise, compared to the one that were not successful? And about the throughput. How many requests do I have per second overall? And we need these metrics, of course, for our platform. So it's very interesting to know, hey, we have 99.999% availability yesterday. That's really nice to know. But it's even more important to also have them on a granular level. For example, have them per API endpoint or per page that you're rendering out. Again, there are tons of tools around there that let you measure these kinds of things. One that we are using is called Graphite, which is a time series database where you can store all these metrics and counters and timers in there. The front end is not so nice, but there are then things like Grafana that you can add up there to make a nicer queryable front end. For scaling, we also use a small daemon called statsd for that. And the setup looks like this, that we have a statsd daemon that is just running on every server. And every application there, just if it measures something, like some operation took 100 milliseconds, it will send this measurement to the local statsd daemon over an UDP request, and then the statsd daemons will batch all of that and then write this to Graphite. Of course, there are also other solutions there. You can look into Prometheus or hosted solutions where you can pay per metric or per that you're saving there, like Librato or Swasta. It really doesn't matter what you use there, just it matters a lot that you have these kinds of numbers and metrics. And what you can then do there, you can create dashboards over that, that aggregate all this information together. And for that, let's try a demo and show you how this looks like in the browser live. I'm cheating a bit because I already prepared that and loaded the pages before. So what we are seeing here is, yeah, you can see this awesome. It's just like, for example, the metrics for one page. It's called the project's detail page. And you see here the latency, how it developed the last day in the different percentiles. So kind of like page 776 milliseconds, not so great, could be improved. The availability, though, is fairly good. There was like a small dip here, so we should need to look into that. And also, yeah, it's actually not a huge throughput page. We have the same thing also for services. For example, we have an authentication service, where you see the same numbers. The latency here is like 5 milliseconds, which is really okayish. Availability is also fine. Throughput is very large because every request needs to be authenticated. And then you can dive down into that in more detail. For example, here for the latency of the page, we can also see on which services on that page it spent a lot of time. And here we see, for example, for some reason, the green thing is here, the rendering. That took a long time. Maybe we can improve that. We also see here the timings for actually measured at the user level in the browser in Europe and North America, and see, okay, wow, this request actually only took like 700 something milliseconds. The user still has to wait 5 seconds for it to load everything and execute all the JavaScript, which is not that great. First paint matrix and so on. You have here in lot more detail. And this is very helpful to see if something is breaking and analyze further why it's breaking and why I have these performance regressions. Okay, let's go back to the slides. Yeah, it's like a screenshot if that didn't work. Of course, you don't want to spend your whole day looking at graphs all the time. Like, I enjoy that, but maybe you don't. Much better is it to also get alerts if something is breaking. We are using, for example, Nagios and CheckMK for that, which just if a certain metric that we defined goes over a certain threshold, I get a text message. So if our availability drops under like 99.998 or something %, I get a text message and I can see, have a look, okay, why is it happening? But in the end, if we build all these detection things, errors still are going to happen because at some point something will break because of the reasons I mentioned before. So also we should invest some time in ensuring that we are handling exceptions as graceful as possible. Because still, of course we have these nice error pages, but this is not a good user experience for the user. So we can make this better. The first thing we can do there is we can create a component, or we can use a component-based front-end framework. What do I mean with that? If we have a look at a page like this, looks nice, like this is a profile page, what we actually can do, we can identify components that are fairly independent from each other. Like you have, for example, the header here, up here. You have this title bar, you have this left column, this right column, that could be one component, but even more granular, you could have this skills and expertise box. That is one component, and even like this bubble here, this from one skill or one expertise could be one component. And what you can then do there, if you have this split up in different small individual components, you can degrade functionality a lot easier. So for example, I simplified this a bit. This could be like the tree of components that we have there on our profile page. If there is an exception happening, or an error happening in the service that provides the data for this about me component, what we can then do is say, okay, the about me component is kind of important because otherwise it wouldn't be there. But if it's not there, it's better to still show everything else instead of just a big error page. So the user doesn't see the about me component, but they can still interact with the rest of the page, which is far more beneficial. What you even could do then is saying, okay, we're not showing the about me component now, but let's maybe wait like 2 seconds, 3 seconds, and then let's do another XHR AJAX request to try to load it again asynchronously. Maybe it's there then. Amazon, for example, is doing this on their shop page quite a bit, even much stricter because they have very low timeout levels, and if something like the comment box didn't render in time, they just don't show it and try to load it afterwards as well. So that's also one way to how they keep their pages fast. There's also, again, tons of ways how to integrate that. Like one thing we can look into that supports this degrading of functionality and having this separate components is React.js. But if you're using other front-end frameworks, this is also fine and this is doable. Another big cause of regressions is, of course, when you change something. And when you change something, it is usually called a deployment. And of course, especially there, errors will happen again. So we should ensure that deployments are as safe as possible. One good way to do this is to use feature flags or feature toggles. Because with that, we can easily decouple the deployment of some code to the actual release of the feature to the user. A feature flag in the end is just a sophisticated name for an if statement. So a feature flag here would be, okay, this expression, for example, this function call is active, returns true if this feature is switched on, if it returns false if this feature is switched off. And then you can have some interface maybe in your web application that is only there for admins, that just lists all the feature flags. And then you can, for example, do something like activating a feature flag for different roles of users in different countries for a different percentage of users. And through that, also do a partial rollout of your new feature. That means when you deploy the code, you wrap it around a feature flag, the new feature. And then if you deploy it, the code is not active yet. It's on there on the servers, but it's not active. Still the old code is active. Then you can just at some point when you feel comfortable, maybe switch this feature flag on only for members of your team and test this out. What you can then do, maybe switch it on for 1% of the users, look at the metrics, look at the error logs, see if anything is breaking. And if anything is breaking, anything is weird, switch it off again directly because it's just one click. So you can also do fast rollbacks through that. So this is a very beneficial thing and really helped us a lot to increase the stability of our platform and increase also the performance of our platform a lot. Also, this is good for A/B testing, conversion measurement, which means also it's fairly easy to sell to product managers if you do it correctly. So I encourage you to think about feature flags. One thing about them, though, is of course it adds a bit of technical debt because you have the old version of the code and the new version in the code base in parallel. So at some point you also need to clean them up again. And if you don't do that, then your code is going to become very messy very quickly. Let's talk a bit more about microservices. Because microservice means you have tons of services running somewhere, and for some reason they have to communicate with each other over the network, usually with HTTP requests. And there you want to also make this service-to-service communication as safe and as stable as possible. Because what can happen there? You have service A talking to service B. Usually everything is okay, like in time it responds with a 200 okay. But distributed systems are hard. In a network, a lot of things can happen. Errors can happen. Hardware failures can happen. So maybe at some point when service A calls service B, you get a 500 back. So you have to handle this kind of. As we saw, if you have a component-based front-end framework, you can handle this in a lot more graceful way. Even worse than getting a fast error back is if you're just getting a very slow response. For example, if service A calls service B, and then after 2 seconds later, you get a response, it's not good user experience anymore. And it's very likely that your users are not going to wait for 2-3 seconds. Especially, it gets worse if you think about that in most microservice architecture, one incoming request from the user probably leads to multiple requests to some services. That can be like 20, 30, 40 for complex pages that you have to do there. That means the incoming request, because of that, if you have some timeouts somewhere, or if you have a performance problem somewhere, can actually, even if it's just like a slowdown from 5 milliseconds to 50 milliseconds, accumulated, that can actually lead to a huge increase of latency for the incoming request, which is really bad. So you should set a low timeout settings when doing HTTP requests. Again, with tools like Istio or so, as you saw earlier, you can do this. And it already does it for you, but also every HTTP client supports setting timeout settings. So if service A calls service B, you know usually this is done within like 40 milliseconds, even in the upper 99th percentile. You can say, okay, let's wait a maximum of 50 milliseconds for this call, and if not, just don't wait for the response anymore. Also, we have to think about high availability. So for that, usually use a load balancer. So that means we not only have one instance of one service there, but multiple instances. And an example here, service A wants to call service C. So it actually calls some load balancer. The load balancer frequently does health checks to every service and then chooses randomly or with an algorithm one running instance of service C and routes the traffic to there. That means also service A does not need to know on which IP address the service C runs. And this load balancer is doing frequent health checks, so it's really asking all the time, okay, hey service, are you still alive? If not, this will be taken, for example, if service C is not alive anymore, this will be automatically taken out of load. You can even improve that whole thing with a thing called circuit breakers. So a circuit breaker works like that. It's basically part of your HTTP library. If service A wants to call service B, it's going through a circuit breaker. Usually, you can think about a circuit breaker like an electric circuit. Usually it's closed, so the current or the requests are just flowing through all the time. And what the circuit breaker does in addition, it counts the amount of successful requests and the amount of failed requests and calculates an error rate because of that. And if the error rate goes over a configurable threshold, for example, like 1% or so, then the circuit breaker will open. So no request, no current is flowing anymore. And then for a configurable amount of time will actually directly throw an exception instead of doing any requests. That is especially good because if that service is running very slowly and having problems, you're just not calling it anymore. So you're saving some time. And if you have a component-based front-end framework, you can much quicker decide, okay, let's just not show this about me box. And then every few configurable seconds, the circuit breaker will let one request through to see, is the service B here alive and working again? If it is, then if the test is not failing anymore, then it will say, okay, I'm closing the circuit now, and let all requests through again. A library to help with that, for example, is called Hystrix for Java, which is built by Netflix. Or even better, if you don't want to change all your services that you're having and implement like a library there, and there are also technology stacks where it's actually very hard to create to include circuit breakers, PHP for example, because you have a shared nothing architecture, and counting the amount of erroneous requests over multiple incoming requests is hard to do in PHP. Circuit breakers are also included in a lot of these new service mesh load balancer things, for example in Linkerd or in Istio. So what you can do there is, for example, if some service wants to call another service, you have a load balancer already in between there for high availability. If you use Linkerd as a load balancer, Linkerd also has an included circuit breaker. So what happens then is that if service A wants to call service B and service B is not available, that directly here the circuit breaker will break and don't let the request through, and directly will respond with a 500 on this request here. So of course we have still the overhead over like a network connection between service A and the load balancer, but still service B has time to recover, won't get any requests anymore, and is much faster than waiting for the slow timeout. You can also do, I was speaking about currents, and then something was weird here. Let's show you something else. Okay. What you also can then do, you can be more sophisticated with that, especially if you're handling traffic spikes. Again, you have this situation here. Everything is fine if service A is calling service B and the circuit breaker is fine because you all get 200 back in time. Now you deploy something. Deployment means change. Change seems maybe something is breaking. So you deploy service C. And what you see then, C is also calling service B, and you see timeouts here, and this service B is going to be overloaded. It's going to respond much slower. So what happens then? Both of these circuit breakers are saying, okay, I'm not letting any requests through anymore because, yeah, this is too slow. The problem is, since you just are putting much more traffic to service B, is that this will not resolve itself. So ideally, you should deploy new instances of service B to make it scale horizontally, or scale the database behind that. What you can do then in a circuit breaker to make this more resilient, you can introduce like a throttling algorithm. So for example, you can say, okay, it's not working if I let 100% of the requests through. But for example, in a circuit breaker, we could say, okay, we only let like 80% of the requests through. It's still bad because 20% of your incoming requests of the user requests are not answered correctly, but at least 80% are. So it's better than just erroring completely. And then you can have like a TCP slow start algorithm there, which says, okay, let's try first if it's working reliably with like 10% of the requests that I let through, and then let's increase it until I see timeouts again or an error rate. What you also can do in addition there is you can set up priorities. So you could also say, I actually know that service A is much more important than service C because that was just introduced, or if service C is not working, it's still kind of fine for the user, whereas service A, that's really important. So I'm letting 100% of requests of service A through, so I'm giving it much more priority than service C that is doing some background batching things anyways, so I only let 10% of these requests through. Of course, still not ideal because service C is there for a reason, otherwise I can just delete it, but it's still better than nothing. And since we are fairly good on time, I also can show you another small demo. Let's see if that works. because I was talking earlier about this whole log management thing, and I can show you how this looks like live on our platform. So this is like a serious error dashboard. Fortunately, we don't have that many serious errors that need to be fixed, like some weird things where some programming error probably. This is a bit older, so maybe hope somebody fixed it already. So we can scroll through here, and for example, if we look at this here, this is a deprecation notice, so not too bad, but we should still fix it. And then you can see here there are tons of fields in addition that we can use. For example, here's a correlation ID, I have some account ID, so this was a cron job, so there's no logged in account. I have an error code which I can look for. I have the file where it was happening, the line, some session ID maybe, the actual request or call, and the complete stack trace in here. And yeah, user IP I also don't have. Let's maybe look at something more interesting. Let's look at this one. So we see here no account ID in here. We see some browser, that it was a Chrome browser, version 60. Again, a correlation ID here. And we also see here the actual exception that happens and some good information how to fix this. Also, we see here all the request headers and another stack trace. Yeah. Also here the browser of the user that did this. So that's a lot of useful information there as well. And then if I had, the VPN connection is not working anymore, if I had, I could also now filter for any kind of these things. By, for example, just clicking on one of these buttons here. Okay, let's go back to the slides. So to sum all of that up, you should use central log management somewhere to save your error logs somewhere, so that you can easily full text search for them with full text. Still have log files as a fallback. Also, please don't start writing log messages directly from your web application to some MySQL database, because that will slow down your application. That's not good, just for logging. You should monitor and measure everything you have, and in a very much granular level, so that you really know, okay, this page, this endpoint took that long on average, even with what was happening within this page and endpoint. You should have alerts on that, on the more important things, so that you don't have to look at dashboards all the time. You should look into graceful exception handling with a component-based web framework, so that you can degrade functionality and not just display an error page all the time. You should look into feature flags to decouple release from deployments, so that you can also quickly roll back to a working version, so that you can do partial rollouts. And you should, if you're using microservices, it's also very beneficial to look into circuit breakers, so that if one of your services goes down, if something is overloaded, that you still limit the impact of it. I will upload the slides to SpeakerDeck, also tweet about this on Twitter on the DevOps Pro Lithuania hashtag. And you also can follow me on Twitter here to kind of get notice of that. If you have any questions, we have enough time to have a couple of questions afterwards. And also, of course, you can, if you don't want to have a question here in front of the audience, you also can just email me or send me a message on Twitter, and I also can answer you there. Thank you very much.